So, last class what we saw was that dt by dr evaluated at r equal to r naught divided by t naught minus t m is basically a constant, okay, basically a constant and not a function of r, right, not a function of r, not a function of x, okay. But we know that dt by dr by definition, right, is a function of both x and r. So, one can conjecture that perhaps dt by dr by t naught minus t mean will be like a function of r only, okay, because t naught minus t m is a function of x. So, dt by dr we evaluated it at one particular point, we saw that it was not a function of both were same functions of x. So, therefore, once you divide one by the other, there is a possibility that we can argue that this will be a function of r only, okay. So, based on this definition, okay, let us define what will be the temperature profile. So, temperature profile will be T naught minus T divided by T naught minus T mean, okay. This is a function of r only, okay. Whereas, however, individually these are functions of x, t is a function of both x comma r, okay. T naught can also be a function of x, got it. But even though whatever be the nature, right, together this is only a function of r, got it. So, together it is a function of r only, okay. So, this will be the definition of temperature in the fully developed regime, right. So, in the fully developed regime this will be the definition of temperature that we are going to use, okay. Now, let us take the very basic definition, okay, that before we go into all these things, okay. We can take the basic definition now, that let us see what can be, what are the different kinds of temperature profiles that we can actually have, okay. So, one will be of course the uniform heat flux case and one will be the uniform wall temperature case, okay. So, we will look at both the uniform wall temperature and the uniform heat flux both, okay, in the subsequent section. So, let us take the uniform heat flux event over here, okay, because that is a little easier to start with. Uniform heat flux, that means the boundary condition has changed basically. So, this is the pipe once again that you have, goes through. So, there is a heat flux, this is Q double prime, this is basically R naught that you have, okay. So, this is a fully developed temperature profile that you have to find out. Q double prime is basically a constant, this is a uniform heat flux case, right, got it, okay. So, we have said nothing about the wall temperature. Here the wall temperature is not a constant, okay. Wall temperature is still given by T naught, but it is not a constant, right. So, that we will see what that wall temperature is. So, instead of defining the temperature in that way, let us first say T x comma r, T naught x, I am writing the functional variation so that you can get an idea, h f r over r naught. That is the definition that we have applied, right. This is a very simple enough definition once again, because T naught minus T m has been basically substituted by Q double prime, that is all, and using the definition of h, right. So, if you recall the definition of h, what is was Q double prime divided by T naught minus T mean, right. Okay. So, if you have to substitute T naught minus T mean, it will be Q double prime divided by h, that is exactly what we have done over here, this particular term, right. This is, there is no difference between this and this, they are essentially the same, only T naught minus T m has been substituted by Q double prime, because Q double prime is a given and it is a constant, okay. That is the only reason, okay, that we have used. So, do not lose the track of this particular thing, okay. So, therefore, dt by dx, right, should be equal to dt naught by dx. When you differentiate it with respect to x, your Q double prime is a constant, this function is a function of r only. So, when you are differentiating by x, the second term just vanishes, right. So, this is the first quantity that you get, right. Okay. Now, again we also know that Nusselt number is of the order 1, correct. Okay. So, therefore, q double prime into d divided by k t naught minus t mean is of the order 1, right, okay, of the order 1. So, therefore, okay, therefore, from this particular case, okay, if this is of the order 1, then what can we say, or dt naught by dx is the same as dtm by dx. If you just take it to the other side and again differentiate it with respect to x, you know q double prime is a constant. So, it becomes dt naught is equal to dtm by dx, right. So, compositely what we get from this is your 2. So, combining 1 and 2, what do we get? We get dtx, right, partial is equal to dt naught by dx, that is equal to dtm into dx, got it. Okay. So, all the slopes are basically kind of the same, right. Now, in addition to this, we already know that dtm by dx is basically 2 by r naught q double prime divided by rho cp into u, right. Okay. This we already know, recall this is the average axial velocity, got it, got it. Okay. Now, this is basically therefore a constant, right, because your q double prime is a constant, u is the average axial velocity which is a constant, okay, and everything else is a constant over here. So, therefore, as we wrote earlier, dt by dx equal to dt naught by dx equal to dtm by dx is equal to a constant, right. This implies that this is a constant as well, right, dt by dx is a constant. So, temperature, this implies that temperature at any r varies linearly with x. Temperature at any r location varies linearly with x. So, therefore, why not take a look at the sample profiles. Okay. So, let us take this is the tube. Okay. So, let us take this is one section, this is another section, these are all in the fully developed regimes. Pull these things down, this is your x1, this is your x2, right. So, the temperature profile is the mean temperature, this is the profile of the mean, this is the full temperature profile, mean temperature will be somehow here, right, that will be the mean temperature, right. So, at a different cross section you will have that there will be some variation, right, okay, and the mean temperature will be somewhat like that Tm at that particular location. So, if you now plot the variation of the mean temperature, you will find that your mean temperature goes up. Okay. So, this is your mean temperature profile, right. The wall temperature, okay, as you can see from that, is also going to go up, again linearly, the slope is the same, right. So, it is also the wall temperature is also goes up. So, it is a linear, both are linear, right. So, the wall temperature goes up linearly, the mean temperature also goes up linearly. Now, as you can see that T naught is definitely more than Tm, that is why we have one over the other, because that is a wall. Wall is the maximum temperature over here, right, maximum temperature over here. So, it will be naturally more than the mean temperature, okay, because of the curvature. You can see the curvature over here and you can easily make out that the wall temperature will be the highest. This is basically T naught, this is basically Tm if there is any ambiguity. Okay. So, that is the wall temperature and the mean temperature. Okay. So, between any two locations x1 and x2 you will see all of them going up like that. Okay. So, therefore, we have established that in the case of a uniform heat flux, these two like follows like two parallel lines kind of thing, right. So, the wall temperature also increases, Tm also increases, right. Okay. Now, let us look at the situation that how this can be now solved in a proper fashion. Okay. So, again the equation is still the same, that dt by dx is equal to d square t by dr square plus 1 over r dt by dr, right. U we already know is given by 2u into 1 minus r by r naught square, where u is basically given by 8 mu dp by dx. Got it? Okay. So, that is the original thing that we said, this was the average velocity that we said, okay, and this was the whole profile of the velocity, right. Also the temperature profile we also defined, that was equal to T naught minus q double prime by h f into f by r naught, right. So, that was the two definitions that we had, right, and r bar is basically can be taken as r over r naught in the normalized variable. Okay. So, based on these quantities, right, okay, we can now reduce, substitute them back in the energy equation. So, it becomes u by 1 by r bar square into 2 into q double prime divided by r naught rho Cp into u. Why can I substitute that? Because dt by dx, this is because dt by dx is the same as dtm into dx, right. That is the substitution that we have made, minus q double prime h into f double prime, right, plus 1 by r bar q double prime by h f prime, okay, where h is given as q double prime divided by T naught by T mean, right. So, this is the very standard equation, okay, or in other words now we can write it as 4 q double prime 1 minus r bar square divided by r naught into k is equal to minus T naught minus Tm into f double prime minus 1 by r T naught minus Tm into f bar. Okay. Now, all this f prime is basically given as df by dr. So, you can convert them to the corresponding dr bar coordinate system. So, that is fairly easy to do. Okay. And you can also introduce Nusselt number in the mix, because Nusselt number is given by, as you know, h d by k. Okay. So, based on that, okay, what we can do is we can write the full equation now. Okay. So, I will do one more step so that you get a feel. Or d square f dr bar square plus 1 over r bar df by dr bar 2 hd by k into 1 minus r bar square, right. So, this can be further written as minus 2 into Nusselt number into 1 minus. Okay. Okay. So, I have skipped a few steps, but you can easily follow that what all we have done is converted it to the r bar coordinate system, right. Okay. Now, let us solve this particular equation then. So, d by r bar or df by dr bar is equal to 0 at r bar equal to 0, right. Okay, so this leads to C1 is equal to 0, or df by dr bar minus 2 Nusselt number r by 2 plus 2 Nusselt number r cube by 4. Integrate it one more time, f is equal to Nusselt number into r square by actually this will become 2 now, okay, plus Nusselt number r to the power of 4 by 8 plus C2, right. Okay, now f, as we know, is T naught by T divided by Q double prime by H. Okay, so and H of course we know. So f will be equal to 0 at r bar is equal to 1, right, because it will be the wall at that particular point. So therefore C2 will be equal to, okay, half minus 1 by 8 will be equal to Nusselt number 3 by 8. So therefore the total form of f will be Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8, right. So that will be the total expression that we will get, okay, for f, okay, because f is the thing that we have to solve, okay, utilizing the boundary conditions that we just now mentioned, right, that f prime is equal to f equal to 0 at r bar equal to 1. Okay. Now that we have it, okay, now let us write the full equation. Therefore your T is given as T naught minus T mean into Nusselt number 3 by 8 r square by 2 plus r to the power of 4 by 8, right. So this is the, if you consider f, if you open up f, so that is what you get, right. So from f, basically from f definition, right. So that is what you are going to get, okay. Now, so of course you can take things. So this t is basically a function of both x comma r, right. Now my original definition of Tm, if you recall, was 1 over r naught into u divided by this was 2 pi to r naught T naught minus T u r dr d theta, okay, right. Do you recall? So that was the original definition of Tm when we actually did it, okay. So therefore T naught minus Tm will now, if you can put the terms in within the bracket, okay, so that means you can integrate out this thing in a little bit of a better way, okay, 2 u 1 minus r bar square r into 2 pi dr, right. That is the equation. So this will give you 4 into 0 to 1 T naught minus T 1 minus r bar square r bar dr bar, right. That is the expression that you will get, okay. So therefore we have basically two terms, okay. One is this, okay, which basically gives you T minus T naught is equal to this, okay. The other one is T naught minus Tm is given as a function of this, right, if you look at it, okay. So therefore what we are going to do now is that we are going to take this definition and substitute it here, okay. So T naught minus T, we are going to substitute it in terms of T naught minus Tm, okay, in this expression. So T naught minus Tm is equal to 4 into 0 comma 0 to 1, again T naught minus Tm, we are substituting it now with the Nusselt number 3 by 8 r square by 2 r to the power of 4 by 8 into 1 minus r bar square r dr bar, right. Okay. So, that is the substitution, right. So, now this gets cancelled, that is because T naught or Tm is not a function of r anymore. So, that you can take it out of the integral. Okay. So, what you are going to get is 1/4 is equal to 0 to 1 Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8 into 1 minus r bar square r bar dr bar, or you take the Nusselt number out because it is a constant by definition. So, the rest of the integration becomes easy. It is basically an integration with respect to r. Okay. So, if you do this integration, do it, you will get 48 by 11, which is 4.36. That will be the answer. This is of the order 1. So, our scaling analysis was correct. The exact value is 4.36, okay, which has come out through this exercise that we followed. So, two things we did. Fr represents what we call the temperature, the fully developed temperature, right. Temperature, right, that we have found out what the fully developed temperature was. If I have to write it once again, you just note this thing down, because these are the findings, like fact findings, is given as Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8, right. And what was f? If you recall, what was f? F was basically T naught minus T by T naught minus Tm, or it can be also written as T naught minus T divided by Q double prime by H, whatever it is, right. So, this is the definition. Second finding is, or that is what we found, that Nusselt number was 4.36. So, essentially you can say f is equal to 4.36 into 3 by 8 minus r to the power of 2 r to the power of 4 by 8, okay, is what is your definition of the temperature profile. Okay. This is all for uniform heat flux case. Okay. So, this is like the corollary, okay, of this particular thing, right. We also found out that the Nusselt number. So, we have found out the exact variation. So, this Nusselt number is of the order 1, as we decided earlier. Okay. We have found out what is the definition of x going to be. Okay. Similarly, we also found out another important thing, that dTm by dx is the same as dt by dx, right, is the same as dt naught by dx, right. So, we said that all the these two temperatures, well, I have not drawn it exactly parallel. This will be T naught, this will be Tm. So, both of these temperatures varies linearly with x, okay, linear functions of x, and this is equal to a constant, linear functions of x, which was a surprisingly interesting tool which gave us this particular thing. Okay. You can also find out what is going to be your mean temperature now, because you have already got the definition of mean temperature. So, you can find out what is your mean temperature profile is also going to be. But utilizing all these things, we have got these three important correlations, or these three important findings out of this entire exercise, right. Okay. So, this is vitally important, because next we are going to look at the uniform wall temperature case. So, this was the uniform heat flux case, and we saw that this is how the temperature profiles vary, this is how the Nusselt number value will be, and this is how the temperatures, the different temperature gradients are related. So, these are the main three. So, this is like a summary that these are the main three events that you should be really bothered about, okay, when you move on to the next. Okay. So, uniform wall temperature, we will start, pose the problem and finish it afterwards. So, uniform wall temperature, okay, this is a very similar thing now, except now that the walls are fixed at a temperature of T naught. Okay. So, T naught is basically a constant, right. okay. T naught is basically a constant, okay, and your dTm by dx is still given by the same thing, q double prime rho Cp into u, okay, and q double prime is basically h into T naught minus Tm into x, right. Okay. So, now so using these two parameters and using our definition that what it can be, okay, we will see in the next class that how this heat transfer for this particular system can be analyzed. Everything else is the same except that the heat flux is unknown over here, only the wall temperature is known. This is applicable regardless, that dTm by dx, and this is also applicable regardless, okay. All of this can be written in that same fashion, right, but except we do not know what is the value of this q double prime going to be, but we know what is T naught, it is a given to us. So, we will see that how this particular problem pans out in the next class. So, we will finish the uniform wall temperature case and we will see where we get to that. Okay, thanks.